Let's do another example, this time using a dependent voltage source. Alright, so what do we have here? We have a 20 volt voltage source, a 2 ohm resistor, a 20 ohm resistor, a 5 ohm resistor, a 10 ohm resistor, a 2 ohm resistor again, and a current dependent voltage source. So this current I phi is the current flowing through this 5 volt resistor in the right hand direction. As always, we must define the reference ground voltage, and the question is, what is the power dissipated in the 5 ohm resistor? So this is the power flowing through this 5 ohm resistor. And we're going to use node voltage to solve this question. So let's do node voltage. Let's first identify the respective nodes. This is we define this one as V1 and that one as V2. V1 and V2. These are the essential nodes, as well as this one. So let's do node voltage. So at V1 we have V1 and the current flowing out of this path. So we have V1 minus this is Vs here. So 20 volts over the 2 ohm resistor. So we have V1 minus 20 over the 2 ohm resistor. So essentially, what is the current flowing out of this node here? And again, here we've defined the reference ground voltage. So V1 minus 0 over the 20 ohm resistor. So we have V1 over 20. And then we have another current flowing out through here. So V1 minus V2 over the 5 ohm resistor. So it's the voltage drop over this resistor divided by the resistance, and that gives us that current. And that is node voltage at V1. Let's do again at V2. We have the analogous current, V2 minus V1 over the 5 ohm resistor. We have again V2 flowing down to the reference ground. So we have V2 over the 10 ohm. And then finally we have V2 minus, this is also another voltage source, call it Vs prime. So we have V2 minus the voltage over here, which is 8 I phi over the 2 ohm resistor. Perfect. Now, we don't only have these two unknowns, we also do not know what I phi is. So I phi in this direction is defined as similarly as we did earlier, V1 minus V2 over the 5 ohm drop. The 5 ohm resistor. So it's the voltage drop over the 5 ohm resistor gives us the current flowing through that resistor. So we have 3 equations and 3 unknowns. Therefore, we can solve this problem. Let's take equation 1. So we multiply out the greatest denominator. This is a useful trick in node voltage because then we get rid of all the fractions. So we have 10 V1, so we're multiplying out by 20. 10 V1 minus 200 plus V1 plus 4 V1 minus 4 V2 equals 0. This is the new form of our equation 1. Let's simplify this one step further. We sum out V1, so you get 15 V1 minus 4 V2 is equal to 200. Now let's do the same with equation 2. We multiply out by the greatest denominator, so that's 10. So then we get 2 V2, so it's 10 multiplied by this, so 10 divided by 5 is 2, so 2 V2 minus to V1 plus V2 plus 5 V2 minus 40 times I phi equals 0. We're going to make this simpler. We're going to sub in I phi, since that we know it. We're going to sub this in minus 40, and we know that I phi is V1 minus V2 over 5 equals 0. So that is minus 8 V1 plus 8 V2. So what we do here, from here, we get 16 V2 minus 10 V1 equals 0. So 1.6 times V2 is equal to V1. So this is useful. Now we have V2 in terms of V1. Then we can substitute this into our first equation to get either V2 or V1. So that is what we do. 15, and we substitute V1 in for V2. Minus 4, V2 is equal to 200. Then we can get V2 simply as 10 volts. And we know that V1 is 1.6 times V2, so V1 is 16 volts. Wonderful. Now we need to know what an I phi we defined as V1 minus V2 over 5 ohms, apologies. So this is 16 minus 10 over 5. 16 minus 10 over 5. Leave it as in the fraction form as 6 over 5 amps. The initial question, what is the power flowing through this 5 ohm resistor? And we can use the power equation. So P of the 5 ohms is equal, we can use I squared R. So 6 over 5 squared multiplied by 5, and we get 7.2 watts. We could have also similarly done V squared over R, which is 6 squared over 5, and we would have gotten a similar, or exactly the same answer. Wonderful. What we've done today is we have defined the node voltage method, which is basically KCL at specific nodes, where we define the current always leaving those nodes, and we get simultaneous equations. And we use the simultaneous equations to find out the voltages at their respective nodes. We did an example, and then we did another example using a dependent source.